So a decade ago, web or content filtering was expensive to conduct at global scale. Today, commoditization has brought career-grade filtering within the budget of most governments and organizations. In this talk, I would like to talk about content filtering technologies, which are actually serving the purpose of a dual-edged sword. Now, content filtering technologies, or filters or DPAs as they're otherwise called, are commercial hardware or software devices that observe network connections primarily for the purpose of enhancing security. But as I mentioned, these filters also sometimes serve a secondary purpose. In the wrong hands, filters are sometimes used for censorship and surveillance. Now, the problem is that there is very little information about how these filters are actually being used. But this information is crucial to collect. Let me highlight why with the example of Netsweeper. Netsweeper is a Canadian filtering vendor that sells high-quality filtering products and also offers other secondary services, such as dynamic categorization of websites and SSL decryption. Citizen Lab, an NGO in Canada, and co-authors of our paper conducted several investigations of the use of Netsweeper products for censorship in many countries after receiving on-the-ground reports. These investigations, which were the result of several years of manual detective work, identified an alternative lifestyles category used by some countries, such as the UAE, to block LGBTQ content. Citizen Lab recognized this as a human rights issue, and after much advocacy, Netsweeper claims to have removed the option to block based on this category. Now, there are several other examples that I could cite here, but there is a takeaway message. Auditing filters can drive change and better regulate the use of these technologies. We want to track the use of different filters across the globe so that their use for purposes like censorship and surveillance can be regulated. But there is an issue with the process that Citizen Lab followed with the case of Netsweeper. Specifically, the issue stems from the fact that filters are everywhere. There are so many filtering products, and they're in so many countries around the world. The reduced cost and ease of availability has put high-quality carrier-grade content filtering within the budget of most governments, including those with poor records in internet freedom. Our overall goal is to gain a global perspective of how filters are being used so that we know what's happening and where to look. Previous work has limitations when it comes to this goal. Like the case of Citizen Lab and Netsweeper, most studies are based off reports from the country and are biased towards measuring the deployments of a few well-known filters. There is also significant manual effort, which usually involves either physical access to a sample filtering device or the assistance of on-site collaborators, both of which are hard to scale at global level. The main challenge that we face is to scale up the process that Citizen Lab has followed with Netsweeper to detect multiple filters around the world. When we were thinking about this problem, we observed that many censorship deployments responded to blocked content with block pages. Now, these block pages aim to inform users that they're trying to access forbidden content. They are also rich with information, like the trademark of the vendor that has manufactured the product or the identity of the actor that has deployed the product. In our study, we explored the idea of using block pages to extract unique signatures and identify censorship filter deployments. Now, it turns out that block pages are actually great identifiers, and their use is also consistent and scalable because vendors and actors rarely have any incentive to change or remove block pages, and identification of filters using block pages is also scalable at the global level, as I will show later in this talk. So to make use of block pages to achieve our goal of globally measuring filter deployment, we have two objectives. First, we have to collect as many block pages as possible from filter deployments. And secondly, we have to identify the filters themselves using those block pages. Let's look at how we can tackle each of these objectives in detail. First, with the objective being to collect the most comprehensive and global data set of block pages from filters, we turn to global censorship measurement techniques. Now, these techniques are more likely to observe block pages. In our study, we used data collected from 3 complementary censorship measurement sources, which together provide extremely high coverage of filter block pages. The first data source that we used is UNI. UNI is a volunteer network testing direct reachability to sensitive sites. Their measurements have in-depth view of censorship, but due to the dependency on volunteers, there is an inherent limitation in scale, and there are also ethical limitations in recruiting volunteers in repressive countries. Remote measurement techniques such as Quack solve UNI's limitation in scale. Quack makes connections containing sensitive keywords in the payload to servers with the TCP echo port open. Ideally, servers should reflect payloads back, but sensors would send a different response. Now, Quack achieves scale with around 36,000 usable echo servers around the world, but Quack does not do measurements on the HTTP and HTTPS ports. And we observed in our study that many commercial filtering deployments only filtered HTTP traffic. To resolve this limitation, we introduced in this paper a new remote measurement technique as a powerful extension to Quack. We call the system HyperQuack because it uses HTTP and HTTPS vantage points, and because it sounds cool. We call the system, the main idea is that the responses from web server software when requesting a domain not hosted on the server is predictable. Let me explain what I mean by this. Let's consider the server somewhere in the United Kingdom. This is actually the server that hosts the NDSS website. Now, from our measurement machine at the University of Michigan, if we ask the server for the NDSS homepage, it is able to recognize this request and send back the correct response. So it's all fine. But instead, what if we ask for the Usenix website? The server doesn't recognize this request, and it's like wrong conference. So it just sends back an error page. Now, this is just a standard error page from Apache. Let's try one more example, asking for zigzag.org, which hosts the CCS website. Again, the server doesn't recognize this request. But the interesting thing is that the server sends back the same error response as what we got when we requested for the Usenix website. Now, we can use this property that the server's response is predictable when asking for a website not hosted on the server. Now, I would like to highlight that there is a dynamic element here. The server error response actually contains the domain that we requested. To account for this and other technicalities, we request several bogus but benign domain patterns, such as using example.com and prepending www or mail. And then from the server response, we remove commonly changing elements, such as the domain requested and the date. Now, if all the responses from the server match for this trimmed down version, we save it as a canonical template of the expected server response. Once we have generated the canonical template, we can now test for censorship. We send a request to the server with a sensitive keyword, such as block.com, and then we compare the response that we received from the server to the canonical template. If the response is different, this is indicative of some sort of interference in the path. I would like to note here that we do perform retries and control tests both before and after a test measurement to ensure consistency. Now, HyperQuack is great because it increases our scale to potentially more than 50 million vantage points. But to reduce the risk to the servers we use for measurement, we only want to select infrastructural servers, that is, servers that are not end-user owned. To that end, we look at all the official websites of internet service providers provided in PeeringDB, and then look up the servers hosting those websites. For example, to select a server in the US, we look at the PeeringDB entry for Comcast, which is corporate.comcast.com, and then look up the server hosting this website. We then add the server to our list of servers we use for measurements. Now, this step actually reduces the number of vantage points that we can use to around 10,000, but it is a necessary pruning step for reducing risk, because we expect these servers to be better able to handle our measurements because they're part of the network. I would also like to note here that we followed all the ethical principles made in the Quack paper. We discussed the study in detail with the community, made it clear that we are running measurements on our website. We also follow the best practices of internet measurement and rate limit and close connections, and make only one measurement at a time to a server. I'd also like to note that UNI obtains informed consent from its volunteers before running measurements. So with our 3 data collection techniques, we performed 2 types of measurements. First, we conducted a wide-scale measurement testing reachability to more than 18,000 websites in the Citizen Lab test list, which is a curated set of sensitive websites. And We conducted the study over 3 weeks, and we also added UNI data during the same period. We also conducted a longitudinal measurement over 3 months, running quack and hyperquack scans twice a week, and we reduced our load to around 2,000 domains in the longitudinal study. Now that we are done with our first objective of collecting block pages, now we want to automate the discovery of filters from this data as much as possible because there are more than 1 million disrupted responses. We worked on the insight that filters often send the same block page regardless of the domain tested. Our iterative classification algorithm recursively finds large groups of HTML pages with the same content and forms groups of block pages that come from a particular filter. We label each group with a unique pattern from the HTML of the block page. Now, iterative classification only groups block pages with the same HTML, but some block pages may contain dynamic HTML, such as the example here that shows the category of the domain blocked. There are also cases in which we observe the same block page in different languages or the same block page with different ads inserted. So we observed that these pages have high visual similarity, so we grouped them using image clustering, specifically using the dbScan algorithm. With iterative classification and image clustering, we tremendously reduced the manual effort, only looking at around 1 HTML pages from 200 groups instead of looking at 1 million HTML pages. So I talked about the 2 objectives, data collection and data analysis. We put these 2 phases together in our framework, FilterMap. FilterMap is a framework that enables continuous, sustainable, and data-driven view of filter deployment. Now, I'd like to note here that FilterMap can use other censorship measurement techniques for data collection and is not dependent on a specific technique. With our 2 smaller objectives resolved, we are now able to achieve our goal of a global view of filter deployment. Overall, FilterMap found 90 block page clusters, where the clusters indicate the vendor that manufactured the product or the actor that has deployed the product. These filters are deployed in many locations in 103 countries and included commercial products, national firewalls, and filtering deployments in ISPs and organizations. I would like to talk a little bit in detail about the commercial filters, which is the largest class of deployments identified by FilterMap. FilterMap identified 15 commercial products in 102 countries. The most popular product, Fortinet's FortiGate service, has a presence in at least 60 countries. And most of these technologies are sold by companies that are headquartered in the US and then exported to other countries, including to countries that have poor records in internet freedom. Specifically, FilterMap found the use of commercial filters in 36 out of the 48 countries recognized by the Freedom House organization as having heightened censorship. These commercial filters were used to target a variety of content, including pornography, gambling, and anonymization tools. FilterMap also found 4 government block pages in Iran, Saudi Arabia, Bahrain, and South Korea. We also found a large number of filter deployments in ISPs, especially in Russia. Of the 90 clusters that FilterMap found, 70 were found during our latitudinal measurements, and 20 additional ones were found in our longitudinal measurements. Our results show that FilterMap is sustainable and can scale to globally track filter proliferation. Now, FilterMap does have a few limitations. In this study in particular, we only look at block pages as they're rich in information, but future work can look at other components of the filter response, such as the certificate and the TCP/IP header. Motivated actors can also try to change their block page to avoid detection, but FilterMap can generate new signatures in that case. In this study, we also do not consider the exact location in the network where the filtering is occurring. FilterMap has shown that the unrestricted transfer of content filtering technologies has led to high availability, low cost, and highly effective filtering techniques becoming easier to deploy and harder to circumvent. Studies revealing the use of filters for censorship have resulted in million-dollar fines for vendor compliance violations and have motivated further regulatory control. We are maintaining FilterMap as a source of longitudinal data and are collaborating with NGOs such as Citizen Lab to understand the proliferation of filters used for censorship, highlight policy and social responsibility issues, and adding accountability to filter manufacturers. So to summarize, it is very important to collect information about the use of dual-use technologies such as filters for censorship. In this study, we developed FilterMap, a framework for semi-automatically measuring filtering deployments continuously and sustainably. FilterMap found widespread use of filters for blocking access to content, and we make all of our data and results publicly available at this URL. With that, I'd like to conclude and open the floor for questions. Thanks.
So I have a question.
Yes.
You said now that all of these deployments make it more difficult to evade censorship. Why do you think that is the case? Are all of them different? Is not the fact that actually different countries use the same type of filters make it easier for us to design defenses?
So by the sense that when I say it's hard to evade censorship, I just mean that these filtering technologies have really high quality of filtering. That they block, these DPI devices block based on specific keywords. We even see them block HTTPS traffic. That is, somehow they're trying to fingerprint what HTTPS traffic is actually going through. So since filters have this kind of advanced technology, it becomes the same cat and mouse game that we were talking about for circumvention tools to then upgrade their technology. But yes, it does make it easier for circumvention websites to, if all the filters are doing the same kind of censorship, it does make it easier for them to do the same kind of circumvention.
Any more questions? Then let's thank Ram again.
Thank you.